Hey everyone, welcome back, and let's write some more neat code today. So today let's solve the problem contiguous array. We're given a binary array of nums, meaning it just consists of 0 and 1 in the input array, and we want to return the maximum length of a continuous subarray with an equal number of zeros and ones. Thinking about subarrays, the immediate thing that I personally think of is how many subarrays does an array of size n have? It has n squared subarrays. So something like this, where let's say this is the input, we have a subarray here, here, here. Basically, we have n subarrays starting with the first element. Then we have roughly n subarrays starting with the second element, and etc., etc. So it's going to be n squared if we want to check every single subarray. So this is kind of our benchmark. Any solution we get should be better than an n squared solution if we can find one. With this type of problem, what I immediately try to do to optimize it is try something like maybe a sliding window. Is there a pattern here where we can intelligently kind of shift our window? And in this case, actually, there's not. And let me tell you why. Suppose we have this input array. We're counting the number of zeros and the number of ones. When we start, we have 1, 1, and then we get 2 ones, and then we get 3 ones by the time we're over here. Obviously, the number is not equal yet. Now, we get to a point where we have a 0, and then we get a second 0. At this point, even though the number of these is actually not equal yet, there actually are a couple valid solutions. First of all, this is what we've seen so far, but this is a valid solution. It's of size 2. This is a valid solution. It's of size 4. This is our result so far. But if we were to try to do this with the sliding window, you tell me, how do we know if we should try to shift our window? How do we know if we should chop this guy and then shift our pointer over here? Because that is a possibility. Everyone, welcome back and let's hash map here. Okay, let's go to understandable these are, but and subtract the count of 0. You could do it the other way if you want to. It doesn't really make a difference. Just got to be consistent about it, though. Now, let's iterate over the input. Let's say for n in nums. And it turns out that we're actually going to need the index as well, because that's kind of what we're mapping it to. So let's do that at the beginning. Enumerate this so that we can get the index and the number at the same time. So now, what we're going to do is say if n is equal to 0, let's increment the number of zeros. And if n is equal to 1, let's increment the number of 1s. Before we go further, I do want to quickly mention that you notice we're keeping track of the 1s and 0s, but we're not really using both of these very much. Like, we're not using them individually. We're only using them kind of together. So if you really wanted to, you could actually just have a single variable for both of these. Perhaps with 1s, you could increment that variable, and with 0s, you could decrement that variable. But for simplicity, I'm going to kind of keep it like this. I think being explicit is probably more helpful for beginners, but let me know if you'd rather me show the other solution. But now, let's check something. Let's first calculate 1 minus 0. And what we want to know is if this is not already in the hash map, let's put it in the hash map because we only want the first one. So if this is not in diff index, let's add it to diff index, and we will map it to the last index, of course. Okay, now there's a couple things. I mentioned earlier that there's kind of two cases. The first case is if they're equal. If 1 is equal to 0, the counts are equal. And that's easy because we know at that point the result is just going to be 1 plus 0 because we know this is definitely the longest subarray that we've seen at this point because it starts literally at the beginning of the array. But the other case, maybe that's not true. Then we want to know. So I'm going to make this an else if. We want to know, does that difference, 1 minus 0, is it already in diff index? And that's because if it is, then we can find the last index that it occurred at and then subtract it from I, and then we'll get the size of our window. Then you kind of realize if you just like glance up at the code that we don't really need the else if here because we literally did that here. It must be inserted by the time we get here. We don't even need the else if. We'll just change this to an else. So we're guaranteed that this diff exists in the hash map. Then what we're going to do is get the index of it. I'll just call that this. And then we'll say diff index, get that target diff, which is just 1 minus 0. Then to get the size of the window, let me just make sure all the code is visible. We're going to set the result. Now we're going to set it equal to the maximum because at this point we're not guaranteed that this is the largest window like we were up here. So here we're going to set this to be result or set it to be I minus the index. In some cases, this might end up being 0 because if this was the first time that we're seeing this, then we're literally just taking I minus I, and that's 0, of course. But in some cases, it might be a large number. This is the entire code. Let's run it to make sure that it works. As you can see on the left, yes, it does. If you're preparing for coding interviews, check out neetcode.io. Thanks for watching. I'll see you soon.
Hello, and if you're given this coding question during the interview, you're going to have a rough time. So given an array of zeros and ones, return the length of the longest subarray with equal numbers of zeros and ones. Let's say we're given this array, we have the following subarray with equal numbers of zeros and ones, so we can return its length 6. Let's go over the thought process. What we can do is to keep track of the count. When we see a 0, we will decrement the count. When we see a 1, we will increment the count. We can see that if the count ever reaches 0, we have the same number of zeros and ones. To better visualize this, we will plot the count and the index. Now let's say we have the red dots to represent the count at each index, and we have the following where the count is equal to 0. By calculating the difference between the indices, we can find the length of the subarray that contains the same number of zeros and ones. Now this does not only apply when count is equal to 0. When count are equal, we can also find a subarray that contains the same number of zeros and ones. We will need a quick way to check for the count and index. What we can do is to create a hash map to keep track of the count and index. Let's implement the function find max length, take an input array, create the map, keep track of the maximum length and the count, put 0 and -1 into the map as a base case. Iterate through the indices. If the element is equal to 0, increment count by -1, else increment by 1. If the map contains the count, update max length if the current subarray is longer, else put count and index into the map, return max length. If you're given this
Hey everyone, welcome back and let's write some more neat code. Set it to be I minus. Hey everyone, welcome back and let's write some more neat code today. So here we're going to set this to be result or end up being taking I minus our code. Let's run it to make sure that it works. As you can see on the left, yes it does. If you're preparing for coding interviews, check out neetcode.io.
Hey everybody, this is Larry. This is day 4, and here yet a similar problem. Is that I get stuck thinking about zero, Frank, 6 table, and linear time.
Hello everyone.
Hey everyone, welcome back, and let's write some more neat code today. So today let's solve subarray sum equals k. So simply we are given an array of integers nums, and we are given a target integer k, and we want to return the total number of contiguous subarrays which sum up to the value k. This is our target value. So how many continuous subarrays sum up to 2? Well, we have one subarray with the first 2 elements, and then we have a second subarray with the last 2 elements. That's 2. How many different subarrays sum up to target value 3? Well, we have one subarray from the beginning, and then we have another subarray at the end. Now let's think about the brute force approach first. That's going to be n squared. Why is it going to be n squared?
Hello and welcome. Today we're doing another question from LeetCode 75, a really good playlist if you are interview prepping. And I have the entire playlist linked down below if you do want to follow along. So what is this question? It's called maximum average subarray 1. And you were given an integer array nums consisting of n elements and an integer k. Find a contiguous subarray whose length is equal to k that has the maximum average value and return this value. So example 1, we have the following inputs and k equals 4. So a contiguous subarray of size 4 that has the highest average. And that is achieved by this subarray over here, 12, -5, -6, and 50. That sums to 51. And dividing that by 4, we get 12.75. Example 2, we have just 5 and our k is 1, so the average is just going to be 5 by itself. Now, this question is actually pretty simple, but let's take a look at example 1 to see exactly what we want to do. So I have my input nums over here, also the indices up top, and k equals 4. Now I know I want to find subarrays of size 4 with the maximum average. So what I'm going to do is just start off with a size of 4. This is going to be my first subarray, and continue making subarrays of that size k, and just find my max sum. We don't really need to find the average every single time because whatever subarray has a max sum is also going to have the max average. So in the beginning, I'm going to define my current sum and my max sum to both be that initial subarray of size k. So my current sum equals my max sum, which equals the sum of nums up until index k. Now this is going to go up until not including k because it's not inclusive. So index 4 is not going to be included, which is exactly what we want because it's going to go from index 0 to 3 because this is Python and it is going to be 0 indexed. We go from 0, 1, 2, 3. So right now our current sum is going to be 2 and our max sum is also 2. It's just 1 plus 12 minus 5 minus 6. It's coming from this first subarray of size k. And we want to iterate through our input nums. So for I in range length of nums, we want to continue making subarrays of size k. So our next subarray of size k, instead of starting from 0 going to 3, is going to start from 1 and go to 4. We're still including numbers 1 to 3. The only difference is we're now including this index over here and not including this index over here. So what we can do is just subtract what we have at this value and add what we have over here. So from our current sum, what we're going to do is subtract what we have at index I. So nums of I, which is 0. Now, since we are subtracting one index, we no longer have a size of k, we just have these 3. So instead we want to add this index over here. And what we're adding is just I plus k, right? We had index 4, but we're getting rid of index 0. So basically it becomes current sum plus equals what we have at nums of I plus k and minus what we have at nums of I. So our new current sum, what does that equal? We're adding what we have over here, so it's going to be 52. And we're getting rid of what we have at index 0, so it's going to be 51 for our current sum. And we also want to update our max sum to be the max of what we have in max sum so far, and our new updated current sum. So now max sum is also going to be 51. Now we go back in our for loop and do the same thing again. We were just at index 0 for I, but now we're at index 1. And we want to do the same thing again, right? To our current sum, we're going to add what we have at I plus k. K is 4, so we're adding what we have at index 5. So this becomes 54. And we're removing what we have at this index over here, so 12 minus 54. So this becomes 42. And we're done updating current sum. It is now this subarray over here from index 2 to 5. We update max sum, but no updates are needed. 51 is still higher than 42. We go back in our for loop, and I is now index 2. But we actually want to stop, right? We're already at the last subarray of size k. So when do we want to stop? We want to stop at length of nums, which is 6 minus k. We want to stop before we hit index 2, because again, it's not inclusive. So it's going to be for I in range, length of nums minus k. We do whatever computations we need, and in the end, we just return our max sum divided by k. So what is that going to be? It's going to be 51 divided by 4. We know that's going to be 12.75, and that is what we return. So let's go ahead and submit this, and it is accepted. Now talking about space and time complexity for our solution, we go through every single number in our input nums 1, so there's going to be O of n if there are n elements in our
Hey guys, Greg here. Let's solve maximum average subarray, LeetCode number 643. It's a great fixed length sliding window problem. So we're given an integer array of nums, and that has n elements, and we're also given an integer k. We need to find a contiguous subarray whose length is equal to k that has the maximum average value and return this value. So this example Hey guys, Greg here. Let's talk about a popular algorithm known as recursion. Now to illustrate this idea, let's talk Hey guys, Greg here. Today let's talk about two important data structures, namely heaps and priority.
queues. And let me just get this out of the way right at the beginning. These two things basically mean exactly the same thing. Whether someone says a heap or a priority queue, they're really referring to the same data structure. Okay, so a heap or priority queue is actually a particular type of binary tree. Now I'm going to draw a binary tree, although it's not going to be a heap quite yet. Okay, so this is a binary tree, and let's remember that you could actually represent this as an array. And I'll actually do this a little differently than I did the first time. We'll use the first index, and so this is going to be the root, which is 2, and then we'll have the next two children, 5 and 0 here, so this will be 5 and 0, at positions 1 and 2. And then in general, the formula is that for any index I, its left child, if it exists, will be at 2 times I plus 1, and its right child is
Hey everyone, welcome back, and let's write some more neat code today. So today let's solve the problem, take gifts from the richest pile. The idea is we're given an array of gifts. They are going to be integers. I guess in this example, we have this array with 5 values. They're all positive, and I think we can expect that they're all going to be positive or 0. We probably can't have a negative number of gifts. And speaking of gifts, each of these numbers actually represents a pile, and the number itself tells us how many gifts are in that pile. And every second, we are able to perform an operation, which includes this. We can pick one of these piles, the one that has the max number of gifts. If there are multiple, we can choose any of them. So if there is a tie, like we have 2 that have 100, we can choose any. And what we want to do with that number is leave behind the floor of the square root. What does that mean? Well, we have 100, so take the square root of it. And when you take the square root of a number, we might end up with a decimal. This time it's going to be 10, but imagine you had the square root of 10, then you're going to get something like 3.33, and we want to take the floor of that, so we want to round that down. We would end up with just 3.0, so just a 3. That's the number we're going to replace the pile with. Now, after we're done with that, specifically after we're done performing this operation exactly k times, which is the second parameter that's given to us. They probably could have mentioned that earlier, but it's actually, for me, easier when they actually mention it when you're actually needing that parameter rather than like mentioning it up front. But sometimes they do that to intentionally confuse you. Either way, that's the problem. How exactly do we go about solving it? Well, so far it seems like a simulation. So that's what you might try. How could we brute force this simulation? Well, find the maximum in an array. That's a linear time operation. And if we have to do it k times, the overall time complexity is going to be n times k. Because every time we're going to have to find the maximum and then replace it with a new value and just keep doing that, you might think, well, can't we just sort the array? Imagine you have an array like this one, 10, 20, and maybe 100. You pick the maximum, you have to scan through, well, I guess this time you don't have to scan through because it's sorted, so we can just go to the rightmost value and update it by taking the square root of it. It's going to be 10, but now the problem is we modified the array, so now it's no longer sorted. I mean, we could take this value and then insert it somewhere in sorted order, but that's going to be a linear time operation in the worst case. So actually, sorting the array doesn't really make the problem any better. But there is a data structure that has a sorted property to it. Can you think of the data structure that I am thinking of? Well, it's called a heap, and specifically in this case, we're going to be needing a maximum heap. This data structure is designed to have like a sorted property, but also be able to add and remove elements from it dynamically. If you're not familiar with heaps, that's perfectly okay. You're probably a beginner, and that's fine. I would head over to NeetCode.io to learn a little bit more about heaps. You can probably check out my beginner's course or some videos on YouTube about heaps. But this is how it's going to work. We're going to have the max heap. We're going to throw all of these values into the heap. We're going to run a built-in method called heapify. It can turn all of these elements into a heap in linear time. So actually, it's faster than sorting. So we do that in linear time, and then we can run the simulation. So k times, we're going to take the maximum. So this time we're going to take 100, remove it from the heap. So now we have 100. We're going to square root it and floor it, and we'll have 10, and then we'll take 10 and add it back to the heap. So we replace the 100 with 10. We'll just keep going like that. So now we have 64. I think when you square root that, it'll become 8. Now the biggest is 25, same thing. And now we do 10, and then floor it, so it'll be 3. And then you do, I guess we've already done actually 4 runs of the simulation. So now that we are done, what we actually want to do is return the number of gifts that are remaining. So basically just take all the remaining values and sum them up. So whatever's in the max heap, you can just sum up the values. So assuming I did this correctly, we should have 8 plus 9 plus 3, that's 20, plus 5 and 4, that's 29. So that does look correct. So we're pretty much ready to code this up now. In terms of the time complexity though, pushing and popping from a heap is not linear time, it's actually log n time, where n is the size of the heap. So we're doing that k times, the overall time complexity is going to be k log n. Not too bad. Space complexity is going to be big O of n because we're adding all the elements to the heap. One last thing that I want to quickly mention is when we take these values and add them to the heap, we're actually going to make them negative because Python, unfortunately, does not have a max heap built in, but we can get around that by making all the values negative. Here's an example real quick. If I have negative 100 here, negative 25, and let's say negative 64, I'm going to pop from the heap. Since this is actually a min heap under the hood, what's going to happen is we're going to end up popping the smallest value. That's negative 100. After we pop it, let's take the absolute value of it or just multiply it by negative 1, and that'll make it positive. Then we'll have positive 100. Then we're going to square root it and then take the floor of it, which is going to give us 10. And then when we add it back to the heap, we're not going to add positive 10. We're actually going to add a negative 10 because we want this to actually act as if it were a max heap. And by changing all the values to negative, we can basically do that. So in terms of coding, there's actually not much to do. First, we want to take this array of gifts and turn it into a heap. Python allows you to do this, heapq.heapify, and then pass in the array, and it'll turn it into a heap. Like basically, it will leave it as a list, because heaps are implemented with arrays under the hood. You'd probably know that if you've taken my courses or any courses on heaps. But remember, we wanted all the values to be negative before we did that. So the easiest thing to do in Python is to create a new list, just map all these values and turn them negative. So something like this, let's say, or rather, let's just replace gifts. So this is creating a new list and replacing the gifts variable with it. And so I'm going to use list comprehension. So I'm going to do this for g in gifts. For every gift, I'm going to add the negative of it to this list. This is called list comprehension. If you're not familiar with these Python tips and tricks, you can check out my Python for Coding Interviews course. It literally will show you how to do this max heap pattern I'm talking about. But after that, we just pop k times. So for underscore in range k, let's go ahead and do heap q, heap pop from the gifts heap. We will get a value n. It will actually be negative. So to turn it into a positive, I'm going to add a negative sign here. You can do that in Python. In most languages, you would need to do something like this, I think. But in Python, you can get away with this. And so then we want to now push back to the heap a certain value. So back to the gifts heap, we want to push the square root of n, and we made the gifts negative originally. We just take the negative of this. We don't really have to convert these gifts to
Hey, hi.
Hi, hello.
So, what do you do for a living?
Oh, I'm an SEO specialist.
That's great. So, what are the skills required if one wants to get into this domain?
So you
Hey, hi.
Hi, hello.
So, what do you do for a living?
Oh, I'm an SEO specialist.
That's great. So, what are the skills required if one wants to get into this domain?
So you should have an idea about keyword research, backlinking, content optimization, Google Analytics, have an idea about all of these.
Wow, that's a huge amount of skill set. Okay, so what are the salary expectation one can have if they're trying to get into this domain?
So if you're a fresher, you can expect anywhere between 4 to 10 LPA, whereas in a senior role, you can expect anywhere between 11 to 25 LPA or even more.
Wow, that's amazing. Thank you.
Thank you so much.
SEO. I'm a search engine engineer. As a search engine engineer, I'm telling you, you cannot do SEO. If you have great relationships, if you post content, if you tune the structure of the website, if you run ads, if you get reviews, if these are all these things that you can do. If you do these particular things, the net result is SEO. You will rank in Google. You'll rank in Google Maps, you'll rank in queries, you'll rank in ChatGPT, you'll rank in whatever, but the idea that you'll do SEO is like a fat person. If you like tell me, because I have 20 more pounds to lose, you say, you know what, Dennis, just pay me $2,000 a month, and then you'll lose weight.
It's not true.
Why?
You gotta do the work.
Because you don't do weight loss. What you do is you do exercise, you do diet, you do sleep, you do nutrition. These are all these things that you do, and the result of that is you lose weight. I need pictures and videos and reviews. I need the raw ingredients, and that gets put. Just pay me $2,000 a month, and then.
Hey, hi.
Hi, hello.
Since 2009, I've generated hundreds of millions of visitors from Google search. But for the first time in 17 years, I'm questioning everything I know about SEO. SEO used to be simple. You'd find a keyword, post optimized content, get backlinks, and boom, huge traffic, huge income. But that playbook is dead. Why? Mostly because of AI. AI has flooded Google with cheap, mass-produced content. And in response, Google has cracked down harder than ever, erasing perfectly legitimate websites from search results. But that doesn't mean SEO is dead. Google still gets 5 trillion searches a year. That's roughly 100 times more conversations than ChatGPT is expected to have this year. SEO has just evolved, and if you don't evolve with it, you're going to waste months or years on strategies that don't work anymore. So in this video, I'm going to share exactly what I do.
Rachel's a baker who runs her own bakery.
Hey guys, Greg here. Today let's talk about two important data structures, namely heaps and priority queues. And let me just get this out of the way right at the beginning. These two things basically mean exact balanced height n. Okay, so this is currently a binary tree, but it's
question often get asked on the channel is which books to read when you start learning data science. So in today's video, I'll talk about some of the
Really, the first question you should be asking is, what exactly is statistics studying? Now, a lot of people have misconceptions. It's just about like looking at the mean of things and making predictions based on that, looking at standard deviation and variance. That's pretty common stuff. You're going to be using it, but that's not all of what statistics is. You have to learn various programming languages to apply the concepts you've learned. You have to learn math in ways that you've never learned before, like probability. That was a completely new experience for me. On top of this, you're going to learn various modeling techniques to predict into the future. You're going to learn things like survey sampling and how to make a proper survey. All of these things are bashed under the umbrella of statistics, so it's going to be something that you're going to have to keep in mind if you're going to choose this as a major or a minor. Now, for me personally, I go to Penn State, so this experience is going to be a little bit different for everybody depending on where you go and what you choose to do.
Here are the top 10 things you
Probability.
The following content is provided under a Creative Commons license. Your support will help MIT OpenCourseware continue to offer high-quality educational resources for free. To make a donation or to view additional materials from hundreds of MIT courses, visit MIT OpenCourseware at ocw.mit.edu.
Okay, so the course you're currently sitting in is 18650, and it's called Fundamentals of Statistics. And until last spring, it was still called Statistics for Applications, and it turned out that really based on the content, Fundamentals of Statistics was a more appropriate title. So I'll tell you a little bit about what we're going to be covering in class, what this class is about, what it's not about. There's several, I realize there's several offerings in statistics on campus. So I want to make sure that you've chosen the right one. I also understand that for some of you, it's a matter of scheduling. I need to actually throw out a disclaimer. I tend to speak too fast. I'm aware of that. Someone in the back just do like that when you have no idea what I'm saying. Hopefully, I will repeat myself many times. So if you average over time, you'll see that statistics will tell you that you will get the right message that I was actually trying to send. All right, so what are the goals of this class? So the first one is basically to give you an introduction. No one here is expected to have seen statistics before, but as you will see, you're expected to have seen probability, and usually you do see some statistics in a probability course, so I'm sure some of you have some ideas, but I won't expect anything. And we'll be using mathematics, right? It's a math class, so there's going to be, a bunch of equations, not so much real data and, statistical thinking. We're going to try to provide theoretical guarantees. So if I have two estimators that are available
The following content is provided under a The following content is provided under a Creative Commons license.
I'm going to tell you how to go from the application to the point you need to be, but I will certainly describe to you what point you need to be at if you want to start applying statistical methodology. Then once you understand what kind of question you want to answer, do I want a yes, no answer? Do I want a number? Do I want error bars? Do I want to make predictions 5 years in the future? Do I have side information or do I not have side information? All these things based on that, hopefully you will have a catalog of statistical methods that you're going to be able to use and apply in the wild. And also, no statistical method is perfect. Some of them people have agreed upon over the years, and people understand that this is the standard. But I want you to be able to understand what the limitations are, and when you make conclusions based on data, that those conclusions might be erroneous, for example. All right. More practically, my goal here is to have you ready. So, who has taken, for example, a machine learning class here? Right, so many of you actually, maybe a third, have taken a machine learning class. The goal here will be to take you, so statistics has somewhat evolved into machine learning in recent years, and my goal is to take you there. So machine learning has a strong algorithmic component, so maybe some of you have taken a machine learning class that displays mostly the algorithmic component, but there's also a statistical component, right? The machine learns from data, and hopefully, so this statistical track, and there's some statistical learning, which are statistical machine learning classes that you can take here, so they're offered at the graduate level, I believe. But once you take those classes, I want you to be ready to be able to take those classes having the statistical fundamentals to understand what you're doing, and then you're going to be able to, expand to broader and more sophisticated methods. So lectures are here from 11 to 12:30 on Tuesday and Thursday. Victor Emmanuel will also be, and you can call him Victor, will also be holding mandatory recitation. So please go on Stellar and pick your recitation. It's either 3 to 4 or 4 to 5 on Wednesdays, and it's going to be mostly focused on problem solving. They're mandatory in the sense that, we're allowed to do this, but they're not going to cover entirely new material, but they might cover some, techniques that might save you some time when it comes to the exam. So, you might get by, so, attendance is not going to be taken or anything like this, but I highly recommend that you go because, they're mandatory, so you cannot really complain that something was taught only in recitation. So please register on Stellar for which of the 2 recitations you would like to be in. They're capped at 40, so a total of 11 problem sets. I realize this is a lot. Hopefully we'll keep them light. I just want you to, not rust too much. The 10 best will be kept, and this will count for a total of 30% of the final grade. They're due Mondays at 8 p.m. On Stellar. And so this is a new thing. We're not going to use the boxes outside of the math department. We're going to use only PDF files. So you're always welcome to type them and practice your LaTeX or Word typing. I also understand that this can be a bit of a strain, so just write them down on a piece of paper, use your iPhone, and take a picture of it. Dropbox has a nice new, so try to find something that puts a lot of contrast, especially if you use pencil, because we're going to check if they're readable. Letter size, this is not a strict requirement, but I don't want to see thumbnails either. You are allowed to have 2 late homeworks, and by late I mean 24 hours late, okay? No questions asked, you want on this cheat sheet. All right, the final will be decided by the registrar. It's what orthogonal vectors are, and I'll remind you about, so we'll talk about eigenvectors and eigenvalues, but I remind you all of that. So this is not a strict prereq, but if you've taken it, for example, it doesn't hurt to go back to your notes when we get closer to this chapter on principal component analysis. The chapters as they're listed in the syllabus are in order, so you will see when it actually comes. So there's no required textbook, and I know this is a bit of a, I know you tend to not like that. You like to have your textbook to know where you're going and what we're doing. I'm sorry, it's just this class. Either I would have to go to a mathematical statistics textbook, which is just too much, or to go to a more, engineering type statistics class, which is just too little. So hopefully the problems that will be enough for you to practice the recitations. We'll have some problems to solve as well, and the material will be posted on the slides. So you should have everything you need. There's plenty of resources online if you want to expand on a particular topic or read it said by somebody else. The book that I recommend in the syllabus is this book called All of Statistics by Wasserman, mainly because of the title. I'm guessing it has all of it in it. It's pretty broad. There's actually not that many. It's more of an intro grad level, but it's not very deep. But you see a lot of the overview. Certainly, what we're going to cover will be a subset of what's in there. So the slides will be posted on Stellar before lectures, before we start a new chapter, and after we're done with the chapter with the annotations, and also with the typos corrected, like for the exam. So there will be some video lectures. Again, the first one will be posted on OCW from last year, but all of them will be available on Stellar. Of course, modulo technical problems, but hopefully this is an automated system, and hopefully it won't work out well for us. So if you somehow have to miss a lecture, you can always catch it up by watching it. You can also play it at speed 0.75 in case I end up speaking too fast, but I think I've managed myself so far. All right, so just last warning. All right, so why should you study statistics? Well, if you read the news, you will see a lot of statistics. I mentioned machine learning, it's built on a lot of statistics. Statistics is now, if I were to teach this class 10 years ago, I would have to explain to you that, data collection and making decisions based on data was something that made sense, but now it's almost, in our life, we're used to this idea that data helps making decisions, right? And so people use data to conduct studies. So here I found a bunch of press titles that I think the keyword I was looking for was study finds if I want to do this. So this I actually did not bother doing it again this year. This is all 2016, 2016, 2016. But the keyword that I look for is usually study find. So a new study find, traffic is bad for your health. So we had to wait 2016 for data to tell us that. And there's a bunch of other slightly more interesting ones. For example, one that you might find interesting is that the study finds that students benefit from waiting to declare a major. Now, there's a bunch of press titles, one that studies, one in the MIT News that studies, finds brain connections key to reading. And so here we sort of have an idea of what happened there, right? Some data was collected, some scientific hypothesis was formulated, and then the data was here to try to, prove or disprove the scientific hypothesis, right? That's the usual scientific process. And we need to understand how the scientific process comes, because some of those things might be actually questionable. Who is 100% sure that study finds that students, do you think that you benefit from waiting to declare a major, right? Maybe some of you, I mean, I would be skeptical about this, right? I would be like, I don't want to wait to declare a major. Maybe this study, so what kind of thing can we bring? Well, maybe this study studied people that were different from me. Or maybe the study find that that this is beneficial for a majority of people. I'm not a majority, I'm just one person. There's a bunch of things that we need to understand what those things actually mean. And we'll see that those are actually not statements about individuals. They're not even statements about the cohort of people that actually look at. They're statements about a parameter of a distribution that was used to model the benefit of waiting. Right, so there's a lot of questions and there are a lot of layers that come into this, and we're going to want to understand what was going on in there and try to peel it off and understand what assumptions have been put in there. Even though it looks like a totally legit study, out of those studies, statistically, I think there's going to be one that's going to be wrong. Well, maybe not one, but there might be. If I put a long list of those, there would be a few that would actually be wrong. Okay, if I put 20, there would definitely be one that's wrong. So you have to see that every time you see 20 studies, one is probably wrong. When there's studies about drug effects, it would be out of the list of 100, one would be wrong. So we'll see what that means and what I mean by that. Okay. So of course, not only studies that make this discoveries are actually making the press title, there's also the press that talks about things that make no sense. So I love this first experiment, the dead salmon experiment. So actually, it was a graduate student came to a neuroscience poster session, pulled out this poster, and explained the scientific experiment that he was conducting, which consisted in taking a previously frozen and thawed salmon, putting it in an MRI, showing it pictures of violent images, and recording its brain activity. And he was able to discover a few voxels that were activated by those violent images. And can somebody tell me what happened here? Was the salmon responding to the violent activity? So basically, this is just the statistical fluke, right? That's just randomness at play. There's so many voxels that are recorded, and there's so many fluctuations, right? There's always a little bit of noise when you run those things, that some of them just by chance got lit up. And so we need to understand how to correct for that. In this particular instance, we need to have tools that tell us that, well, finding 3 voxels that are activated for that many voxels that you can find in the salmon's brain is just a too small of a number. Maybe we need to find a clump of 20 of them, for example. All right, so we're going to have mathematical tools that help us find those particular numbers. I don't know if you saw this one by John Oliver about hacking, or actually it said p-hacking. And so basically what John Oliver is saying is actually a full length, like there's long segments on this, and he was explaining how, there's a huge, there's a sociology question here about how there's a huge incentive for scientists to publish results, right? They're not going to say, you know what, this year I found nothing. And so people are trying to find things, and just by searching, it's as if they were searching for all the voxels in a brain until they find one that was just lit up by chance. And so they just run all these studies, and at some point one will be right just out of chance. And so we have to be very careful about doing this. There's much more complicated problems associated to what's called p-hacking, which consists in violating the basic assumptions, in particular looking at the data and then formulating your scientific assumption based on the data, and then going back to it, it doesn't work, let's just formulate another one. And if you start doing this, all bets are off. Okay, so actually the statistics, the theory that we're going to develop is actually for very clean use of data, which might be a little unpleasant if you spent, if you've had an army of graduate students collecting genomic data for a year, for example. Maybe you don't want to say, well, I had one hypothesis, didn't work, let's throw all the data to the trash. And so we need to find ways to be able to do this, and there's actually a course being taught at BU. It's still in its early stages, but something called adaptive data analysis that will allow you to do these kind of things. Questions? Okay, so of course statistics is not just for you to be able to read the press. Statistics will probably be used in whatever career path you choose for yourself. So, it started in the 10th century in Netherlands for hydrology, right? Netherlands is basically in the water and the sea level, and so they wanted to build some dikes, but once you're going to build a dike, you want to make sure that it's going to sustain some tides and some floods. And so in particular, they wanted to build dikes that were high enough, and but not too high. You could always say, well, I'm going to build a 500-meter dike, and then I'm going to be safe. You want something that's based on data, right? You want to make sure. And so
7 years ago, I made a bet.
This video was brought to you by Squarespace. There is one
and enrolled in a master's program in biostatistics. At the time I'm reading this, I'll soon be graduating with a PhD, and I'll be working full-time as a statistician in a few weeks. So, I guess the bet paid off. And you might be contemplating a similar bet. Is it worth it to get a statistic to start started my master's degree, I'd only ever taken 2 statistics courses. This was during a time that I didn't really take school all that seriously. Like with any new game, I started with an empty skill tree like this one. I've imagined this tree to consist of 3 parts: the core, the shell, and the advanced skills. The core represents the key concepts and ideas that are relevant to first year. Masters and PhD in them here. Learned a lot of course basic what I missed. Let me know in a comment below skills, or to consist of statistics and statistical programming. I think of probability as the branch of mathematics that studies uncertainty. Mathematical statistics might sound a little weird to you. You can think of it as the mathematical theory that underlies statistical methods. Finally, statistical programming refers to programming that specifically deals with the application and implementation of statistical methods. As I've said many times on this channel, statistics nowadays is mostly done on a computer. So programming is how we tell the computer what to do. Statistics and probability are often paired together, and for a good reason. Statistics builds on the ideas from probability, so it's impossible to separate the two. Despite this, graduate programs will often make probability a separate course from the rest of the statistical courses. This may make sense from a separation of topics perspective, but I've noticed that it tends to make it harder to see all the interconnections between probability and statistics. Since I'm going for the bigger picture, I'm going to interleave these 2 parts of the core together. Statisticians are in the business of dealing with data. On a surface level, data may just seem like information in the form of numbers. We might have an idea of what value data are random events, involve concepts from probability. The main object that we use for random events is the random variable. When we actually make the observation, we'll get a single realization of this random variable. Depending on what our data looks like, these observations may be discrete, aka categorical, or continuous. Random variables have several other objects that can help us characterize them in different ways. First, random variables have functions called probability distributions that describe what data values are likely, unlikely, or outright impossible. Depending on whether your data is discrete or continuous, these functions may look different, but their role remains the same. These probability distribution functions are useful because they let us characterize the random variable without needing to actually observe it. For example, the expectation of a random variable represents a typical value you might see in your data. Expectations are defined in terms of an integral over the probability distribution of a random variable. Similarly, the variance characterizes uncertainty, as measured by how far a random variable can deviate from its expectation. Usually, expectation is measured by how far a random variable can deviate from the variance character. characterizes uncertainty, as measured by how far a random variable can deviate from its expectation. Usually, expectation and variance are what you worry about the most in statistics, but in more niche cases, you might worry about higher moments like the skew or kurtosis. While variance describes the uncertainty in a single random variable, we also have a notion of how two random variables vary with each other. This is covariance. But usually, we talk in terms of correlation instead of covariance, since it's standardized between -1 and 1. So far, we've just been talking about a single data point, but we all know that we need more data than that to do anything useful. Multiple observations give us a data set. Typically, we assume that each of these observations in our data set come from the same underlying random variable. That is, our data is IID, independent and identically distributed. This assumption is required for several important theorems that will come up later. Having a distributed random variable, that is, our data is IID, independent and identically distributed. This assumption is required for several important theorems that will come up later. Having more data gives us more information about the underlying random variable, but it brings another problem: presentation. If we've observed n data points, what is the best way to talk about them? I wouldn't want to list out each individual value every time I want to talk about the data. Instead, we condense our data into a single summary value called a statistic. A statistic is just a function of the data. Functions or transformations of random variables are also random variables in and of themselves, so statistics have all the same objects associated with them. A generic statistic is just a function of the data, but different types of statistics have different uses. Some statistics are called estimators. They act as estimates or educated guesses for important values related to the random variables that generated them. Then there are test statistics, which are used to conduct hypothesis tests. Hypothesis tests are how statisticians make data-driven decisions in the face of randomness in the data. Some test statistics are derived from estimators, so these ideas aren't mutually exclusive. For both estimators and statistics, we're interested in characterizing the probability distribution that governs them. We even give that distribution a special name, the sampling distribution. But characterizing the sampling distribution can be difficult, especially when the underlying data can take on so many different forms. Thankfully, there are theorems that give us nice sampling distributions if we're looking at a particular statistic. For example, the famous central limit theorem tells us that the asymptotic distribution of the sample mean is a normal distribution, and the delta method tells us that some function of the sample mean are also normally distributed. We take advantage of these distributions to derive some useful probabilities and perform these hypothesis tests. My board's getting a little cramped, so I'm going to clean up things so we can start back with estimators. I said that estimators are educated guesses. We didn't really get into what they're trying to guess. When we gather data, we typically have a target group in mind of what we want to study, which we call a population. In practice, we can't gather data on everyone from this group, so we collect data from a sample with a reasonable amount of people. Our goal is to learn about a specific aspect about this population. These characteristics are represented by values called parameters. Because we can't observe the entire group, the exact
Welcome to Normalized Nerd. In this video, hello people from the future, welcome to Normalized Nerd. In this video, I want to talk about covariance. But why should you learn this? Well, first of all, covariance is inevitable in the computation of correlation, and covariance matrix is a very useful tool in matrix decomposition, which is of great importance in dimensionality reduction and in other machine learning applications. At the end of this video, I will leave you with a nice animation, so make sure to watch this video till the end. I hope you are super excited, so let's get started. We are going to start from the beginning. Here's our one-dimensional dataset, and we want to find the variance of this data. Well, variance is a measure of how much concentrated or scattered the points are around the mean. We compute this by adding the squared distances of all the points from the mean. Then we divide the sum by n minus 1. Why not n? Well, that I will explain in some other video. Here, the variance turned out to be 142.4. Now, let's take this to the next level. I'm assigning another number to each of the points to make the dataset two-dimensional. So now we are dealing with two variables. So far, we know the x variance of the points. Similarly, we can also compute the y variance. And the y variance is 25.9. Now, we have both x and y variance, but these two alone don't say much about the distribution of the data in 2D. What I mean to say is, by looking at the plot, we can clearly see that there's a trend. As x increases, y also increases, but we can't infer this trend or relation from the x and y variance values. For example, take this set of points. The x and y variance remains the same, but the orientation or the trend is completely opposite. Here comes the covariance between x and y. The formula looks like this. It says for each point, compute the difference between its x coordinate and the x mean, and the difference between its y coordinate and y mean. Then multiply them. Let's see this in action. After doing this for all the points, you can see that the points lying in the green region give positive values, and the points in the red region give negative values. In our case, we have more points in the green region than red, so our sum will be positive, and hence the covariance will be positive. But if we had more points in the red region, then the covariance would be negative. And it's not very hard to see that more positive points mean x and y are increasing together, and more negative points mean x is increasing but y is decreasing, or vice versa. And that's how covariance quantifies the direction of the trend, but it does not say how strong the trend is. And covariance is very sensitive to scaling. Can you guess the range of possible values for covariance? Yeah, it can lie anywhere between negative infinity to positive infinity. Now let's come to the covariance matrix. Along the the trend is.
Even the best dart players never throw.
And covariance is very sensitive to scaling. Can you guess the range of possible values for covariance?
When two variables change together, we say they're related. But how?
Yeah, it can lie anywhere between negative infinity to positive infinity. Now let's come to the covariance matrix. Along the main diagonal, you can see covariance of x with itself and covariance of y with itself. It might seem a little strange, but if you put the same variable twice in the covariance formula, you will find it's just the variance. I'm leaving this as an exercise for you. The other two entries of the matrix are the covariance of x and y. For our case, it looks like this. As I said earlier, covariance only tells you the direction of the trend between two variables. It can't measure the strength of the relationship. To quantify the strength of the relationship, we can use correlation coefficient. And the formula goes like this. Notice that in the numerator, we have nothing but the covariance. And we are kind of normalizing this
throw with perfect aim.
But characterizing the sampling distribution can be difficult, especially when the underlying data can take on so many different forms. Thankfully, there are theorems that give us nice sampling distributions if we're looking at symptotic distribution of the sample mean.
So you're going to be
also
like you want to make sure that it's going to
sustain
sustain some tides and some flood.
So I'm going to clean up things so we can start back with estimators. I said that estimators are educated guesses. Didn't really get into what they're trying to guess. When we gather data, we typically have a target group in mind of what we want to study, which we call a population. In practice, we can't gather data on everyone from this group, so we collect data from a sample with a reasonable amount of people. Our goal is to learn about a specific aspect about this population. These characteristics are represented by values called parameters. Because we can't observe the entire group, the exact value of this parameter is unknown. So this is the thing that we're trying to estimate from data. We usually model the data from the population as coming from some parametric distribution, where the parameter will completely determine the shape of the function and which values are likely and unlikely. By far, the most common examples are the normal distribution for continuous data and the binomial distribution for binary data. We might be interested in estimating the mean of the normal or the probability of success from the binomial. So now we know what an estimator is. Now we need a way to actually make them. That is, how should we use the data we collect to actually
If you're new to the channel, let me break character for a bit. My name's Christian and I'm a PhD student in biostatistics. Parameters as a general complex real world, 1 when the condition inside is true and 0 other. The Bernoulli distribution tells us these events happen with some probability p, distribution to model the in batches. There's always which we denote sigma squared x's. Since the peak of
If we were looking to understand the spread of player heights in the NBA, we may well use a normal distribution, where the continuous numerical height data from the population of NBA players is distributed symmetrically around the mean. In other words, 50% of the observations lie below the mean and the other 50% lie above the mean. The spread of the data in a normal distribution is represented by the standard deviation. And this is all well and good, but not all data exists in continuous numeric form like height does. Not all data falls symmetrically around a mean, and not always do we have the full population of data to work with. So what do we do in those situations? In this video, we are going to cover the 6 most common distributions that you will come across. So the normal distribution, which we have talked about already, the t distribution, of which we can see several versions of on screen here, and we will talk about exactly what those all mean very soon. We will look at the binomial distribution and the related but simpler Bernoulli distribution. We will discuss the uniform distribution, and we will take a look at the very interesting Poisson distribution. So let's do
construct the guess. The main method that students will learn is maximum likelihood. Estimation. It's not the only way of making a guess, but it is by far the most relevant method to the tools that graduate students learn. We construct the maximum likelihood estimator by taking the probability distribution of the data and using it to construct a function called a likelihood. By picking the parameter value that maximizes the likelihood we have, then theoretically, this should be a good guess. And yes, people have demonstrated that the MLE has great properties for an estimator. It's consistent, meaning that the estimator will get extremely close to the true parameter with large amounts of data. It has a nice asymptotically normal sampling distribution,
StatQuest! Hello, and welcome to StatQuest. StatQuest is brought to you by the friendly folks in the genetics department at the University of North Carolina at Chapel Hill. Today we're going to be talking about sampling a distribution, or getting samples from a distribution. This is something that we do all the time in StatQuest, so I wanted to make a video that we could reference rather than covering the same material over and over and over again. So let's get down to it. Here, we have a histogram of height measurements. Each red dot represents a different person that we measured. The tallest part of the histogram shows the region where measurements are most likely. In this case, most of the people we measured were between 5 foot 7 inches and 6 feet tall. The low parts of the histogram show where measurements are less likely. In this case, we didn't measure many people that were shorter than 4.5 feet or taller than 6.5 feet. We can approximate the histogram with a smooth curve. You guys already know all this from the StatQuest on statistical distributions. What we want to know today is what it means to take a sample from a distribution. All that means is that we use a computer to pick a random number based on the probabilities described by the histogram or the curve. For example, if we wanted to take one sample from this distribution, there's a good chance the computer will pick a value near the middle, where the histogram and curve are tallest. However, every now and then, the computer will return a value from the edges, where the histogram and curve are the shortest. Why would you want to take a sample from a distribution? We do this to explore statistics. The computer can generate lots of samples, and we can plug them into statistical tests to see what happens. Since we know what the original distribution is, we can compare our expectations of what will happen to reality. For example, I could take two samples, where n equals 3, from a single distribution and do t-tests on the samples. In this case, n equals the number of measurements we take within each sample. Since the distribution is the same, the t-test should give me a large p-value. Doing lots of tests will give me a sense of how frequently the t-test successfully gives me a large p-value. If I had two separate distributions, a t-test is supposed to give me a small p-value. If I took lots of samples, I could do lots of t-tests and see how frequently the t-test worked and gave me a small p-value. This would tell me if I needed to increase my sample size or not. Taking samples from a distribution, or multiple distributions, i.e. getting a computer to generate a bunch of random numbers that reflect the probabilities of a distribution, lets us determine what a statistical test is capable of doing without doing much real work. Hooray! We've made it to the end. Tune in next time for another exciting StatQuest.
Hello, and welcome to Python for Everybody, the most popular programming course in the world since 2014. My name is Charles Severance, and I'm a professor at the University of Michigan School of Information, and I developed this course and these materials. Python for Everybody is dedicated to helping anyone learn to program regardless of your background. It has no prerequisites. It does not require math.
With the known expression for the variance. So it's rather easy to calculate probabilities from. And it's asymptotically efficient, meaning that the variance of this distribution reaches the lowest possible value it can take. In a sense, it means that we're making the most of our data and giving ourselves the best chance of making good decisions if we use the MLE. In your courses, it's easy to see the maximum likelihood estimator as just another calculus exercise. For basic problems, the MLE will have a nice exact form, but this won't be the case in general. Instead, you'll need to rely on computers and optimization algorithms like the Newton-Raphson algorithm to get the value of the estimator. There may be other situations that make it impossible to use maximum likelihood directly. Our models might have missing values for data parameters, but we can turn to the EM algorithm to overcome this problem. Some of the more advanced models you learn in the shell are only possible thanks to algorithms like these. I've tried to keep this mapped to the core concepts, but there are so many specific concepts that I've had to leave out just to keep the
visual clean. Mathematical statistics and probability form the theoretical background that graduate level statistics students are expected to have. They can give you a proper sense of when a tool would be useful, and maybe more importantly, when a tool is inappropriate. It still remains that models need to be applied to specific problems. This is where statistical programming comes in. To communicate with the computer, we have to use a programming language. Both of my graduate programs elected to teach the students R, since it's wholly dedicated to statistical analyses, but I've also seen Python offered for elective classes, especially for those focused on machine learning. Most people think of statistics in terms of applied statistical tools like hypothesis tests, regressions, and predictive models, but statistical programming encompasses much more than that. For example, I mentioned earlier that optimization algorithms come into play with maximum likelihood. When a statistician is developing a new method, they're the one that has to translate it from the theory to the actual software that other people can use. From my observation, this is actually a weakness of the programs I've been a part of. Statistics students are not often taught good practices when it comes to developing software, but it's really up to the student to actually pick up this extra knowledge if they want to stand out. Statistical programming also plays a role in testing and evaluating new methods, and this is usually done through Monte Carlo simulations, aka simulation studies. In simulation studies, we can control the characteristics of the data through random number generators. Even though the data is random, having control of this process lets us evaluate how models perform in different settings. This is especially useful for seeing and quantifying what happens when our statistical assumptions are violated. Maybe you've been listening to me talk about all these math and programming concepts, and you're feeling a little behind. That's how I felt when I first started my master's, and I used that memory to hit the ground running when I started my PhD. If you'd like to get ahead, map. One of the first things that students learn is basic hypothesis tests, subset into a tiny map. One of the graduate programs have narrowed them down to a small subset that are considered essential for any statistician to know. Things that students learn is basic capture the essence of that subset into a tiny map. One of the first things that students learn is basic hypothesis tests. For better or worse, hypothesis tests are how we make informed decisions in the face of random data. We use hypothesis tests to decide whether or not a given state of the world, the null hypothesis subset into a tiny map. One of the first things that students learn is basic hypothesis tests. For better or worse, hypothesis tests are how we make informed decisions in the face of random data. We use hypothesis tests to decide whether or not a given state of the world, the null hypothesis, could have reasonably produced the data we saw. The type of data we're dealing with, continuous or categorical, changes the type of test we'll use. If we're dealing with continuous data, you might use a z-test. You might remember that the central limit theorem provides us with the limiting distribution for the sample mean, so we can leverage this distribution to make a hypothesis test. If we can assume that we know the variance of this underlying data, we get the z-test. But more often, we have to estimate it from the data instead. This adds extra variance to the test statistic, which yields the famous t-test. We can also leverage the z-test test to perform hypothesis testing on categorical data as well. This gives us the proportion test. For all these tests, we can easily extend them to the case of a two-sample test, where we're comparing two groups. And these are all easily derived thanks to the properties of the normal distribution. For categorical data, we can turn to the chi-square test and its other variants. These hypothesis tests rely on the assumptions of the central limit theorem to be valid, but real-life data doesn't always let this happen. When this is the case, we may need to turn to a different class of hypothesis tests to allow us to avoid making unreasonable assumptions. This is the world of non-parametric tests. These might require us to ask slightly different questions of the data, but there are well-established one-sample, two-sample, and multi-sample hypothesis tests in this area for both continuous and sample. These might require making unreasonable case, we may need assumptions. This is the world of data. But there are well-established one-sample, two-sample, and multi-sample hypothesis tests in this area for both continuous and categorical data. All these tests together can make decisions that cover an impressive amount of basic research questions, and you'll most likely be helping non-stat people deal with them. The output of hypothesis tests is a decision, and we can measure the quality of these decisions in several metrics. One of the most commonly used ones is type 1 error, which is when you accidentally reject the null hypothesis when it's true. When we consider multiple hypothesis tests at the same time, we might consider the family-wise error rate or false discovery rate instead. Since the true state of the world is unknowable, we won't actually ever know when we commit a type 1 error, but we can set a level to define our tolerance for the probability of doing one. Once this level is decided, we want to maximize our power, the probability of correctly rejecting a null hypothesis when it's actually false. Power is mostly used as a planning tool for research designs, but we'll get back to this later. When we're using a test, we want to make sure that we're using the most powerful hypothesis tests that are available to us. Something you might learn as a PhD student is the concept of most powerful tests, which achieve this goal. What you'll learn down the line is that almost all the tests that we teach to statistics students are some form of these most powerful tests. It's important that other people have proven that these tests have these properties, but it doesn't really change much from a user standpoint. One of the most common types of research questions you'll encounter are about relationships between variables. We want to know if these relationships truly exist, so we have the relationships between variables. One of the most common types of research questions you'll encounter are about relationships between variables. We want to know if these relationships truly exist, so we often derive hypothesis tests based on the estimated parameters for these models. In general, these are called regression models. And the very first one you'll learn in graduate school is linear regression. Linear regression is the simplest regression model we have, and it forms a useful baseline for learning other models. It tells us how the change in the independent variable are associated with average changes in a continuous outcome. And it can easily be dependent variable are associated with average changes in a continuous outcome. And it can easily be extended to multiple variables simultaneously. We estimate the parameters in a linear regression with the famous ordinary least squares estimators. These estimators are known to have a multivariate normal or t-distribution, which we take advantage of for hypothesis tests. Not only do we have this useful distribution, but another theorem, the Gauss-Markov theorem, says that the OLS estimators are the best we have, assuming the conditions for the theorem are right. We may have outcomes that aren't continuous, so linear regression won't cut it here. To account for different outcomes, you'll learn about the generalized linear model, or GLM. If you can assume that your outcome comes from a special distribution called an exponential family, then you'll have access to the GLM exponential family. Statistics, the trade-off between real or very simplistic model to big model. One of the first examples of this in biostatistics is longitudinal data, where a single unit results. One might use a GEE or a mixed effects model to LM, and they both have their pros and cons. Another example of this realism-simplicity trade-off is in the world of survival analysis. Survival up to a given time point looks like a continuous variable, but it has special considerations we need to account for. It's possible for survival data to be censored, meaning we don't actually observe if someone experiences the event we're interested in or not. If we don't account for the censoring, we'll get biased results. Tools like the Kaplan-Meier curve and Cox's proportional hazard model are the main tools that students will learn in this domain. I mentioned earlier that hypothesis testing plays a significant role in regression analysis. This brings up the question for the sampling distribution for the estimates for these models. Besides the GEE, all these models get their sampling distribution from maximum likelihood theory. If you're curious, the GEE also has an asymptotic normal distribution, but it's derived from a different method. When most people think of statistics, I think this is what they have in mind: the analysis of data via hypothesis tests and regressions. But in reality, career statisticians are also in charge of designing the experiments and specifying who, how, and what data we collect in the first place. In biostatistics, this is also known as clinical trial design, but the more general term for it is design of experiments. This is the skill set that earns biostatisticians six-figure salaries, so being skilled here will have big benefits for your wallet. The experiment that most people are familiar with is the randomized controlled trial. You might know it as the A/B test. Randomized controlled trials are important because they allow us to make cause and effect phase 2 trials that will try to figure out if I can really count the number of times that I was asked to. So statisticians play a key role in making type of experiments for a long simultaneously. Another form of experiments that statisticians can learn are adaptive trials. Aside from that, but for simplicity, I'll go with machine learning. I didn't get a lot of machine learning coursework in my master's or my PhD, so I'm not nearly as familiar with it compared to inference. That being said, I'm familiar enough with it to at least give you a general overview. Depending on the kind of outcome you want to predict, there are two types of prediction you can do. Prediction of continuous outcomes is called regression, while prediction of categorical outcomes is called classification. Of course, there are different subcategories for each of these prediction tasks. We'll keep it to these for now. In both of these cases, there are different subcategories for each of these prediction tasks. We'll keep it to these for now. In both of these cases, you gather some data and you use it to estimate a function which will act as your predictive model. There are lots of different types of and you use it to estimate a function these for now. In both of these cases, you gather some data and you use it to estimate a function which will act as your predictive model. There are lots of different types of machine models learning out there, tree-based models, even the simple linear regression, but I won't cover them here. We're just going for big picture. We'd like these predictive models to perform well on data it hasn't seen before, and we summarize this performance into a single number. I'll call this generalization error, since I think it's more descriptive than just test error. This generalization error is based off of some loss function that acts as a measure of how good or bad a model's predictions are. In regression, the mean squared error is an example of a loss function, while in classification, you might use accuracy. To get a sense of how well our model performs in unseen data, we might also split our observed data set into two sets, one to train the model and another to better sense of set of data. In the end, the test error we get is based on the data we saw. We'd still like some mathematical guarantees that our machine learning models will perform well. This is where frameworks like empirical risk minimization come in, the mathematical foundation of machine learning. I thought machine learning was easy before the mathematical foundation of machine learning. I thought machine learning was easy before I learned about this framework, and I quickly changed my mind after that. Machine learning was easy come in, the mathematical foundation of machine learning. I thought machine learning was easy before I learned about the mathematical foundation of machine learning. I thought machine learning was easy before I learned about this framework, and I quickly changed my mind after that. Finally, we come to advanced skills. This is already a long video, so I'll keep it short here since I don't have much to say about these. The fact is, I can't even read a long video to change my mind after that. Machine learning was easy come in, the mathematical foundation of machine learning. I thought machine learning was easy before I learned about this framework, and I quickly changed my mind after that. Finally, we come to advanced skills. This is already a long video, so I'll keep it short here since I don't have much to say about these. The fact is, I can't even really speak to most of these topics because I've never learned them myself. I may have encountered them in a single talk, or may have been mentioned as a single sentence in a lecture, but I'll do my best to give you a brief taste of what advanced statistics look like. When it comes to learning more advanced areas of statistics, what you're really dealing with, high-dimensional early in your coursework. More complex too. Also inference dependent. Founder, exactly. Inferentiation statistics. I hope I've given you a better idea. If you're thinking about going to grad school or you're just self-studying statistics, I hope I've given you a better idea of what you're getting into, so subscribe for more content like this.
Hello. In this video, I want to explain empirical risk minimization, which is one of the main paradigms in machine learning. Most of the machine learning applications in your daily life, such as translation apps or song recommendation systems, are based on empirical risk minimization. Let me explain the basic principles behind empirical risk minimization using the task of predicting the maximum daytime temperature. Consider waking up some morning during winter in Finland and looking outside the window. It seems to become a nice sunny day, which is ideal for a ski trip. To choose the right gear, such as clothing and wax for the skis, it is vital to have some idea for the maximum daytime temperature, which is typically reached around early afternoon. If we expect the maximum daytime temperature of around plus 10 degrees, we might not put on the extra warm jacket, but rather take only some extra shirt for change.
Hey, it's Sergio, fast and well, 1 minute deep into ML. In our previous video, we learned
Before we move on to talk more about graph neural networks, we need to be more specific about what we mean by machine learning and artificial intelligence. Our specific meaning is that ML and AI are synonyms of statistical and empirical learning. These are the subjects we will study in this lecture. Conceptually, an artificial intelligence is a system that extracts information from observations. This is either a downgrade of the meaning of human intelligence or the meaning of artificial intelligence, depending on how much you choose to buy